howdy. This is Mr. Potter. We've emphasized a lot about intervals of convergence, and we've talked about convergence for our Taylor series, for our Maclaurin series, and for our geometric series. But we want to talk about convergence in general, about any power series. In other words, whenever I'm talking about taking a function which is the sum from n equals some value up to infinity of some coefficient times x to the n power, we call this a power series. And so I want to talk about what does convergence mean, and I want to start building up a library of tests that we can do to test if a particular power series is a convergent power series or divergent. That's where we're going to be headed with in this lecture. So first, I want to start off with, what do I mean by convergence? I mean, we talk about these power series functions, but the whole idea is that we're using these power series functions from n equals some k to infinity of some a sub n x to the n being converging to some function of x. And what this means that if it converges on some interval I, that means that for values of x in that interval, f of x is really equal to the sum of a sub n x to the n for n equals k to infinity. And for x not in that interval, this equality is not true. So in other words, this does not equal a sub n x to the n. Now, what's going to happen is there are actually several possibilities when I'm dealing with convergence. The three possibilities we have are, one, that f of x can equal my power series p of x for all real x. In other words, for the whole reals. And it's wonderful when that happens. It's really nice when it happens. It doesn't happen all that regularly. It does happen, for example, with the sine function, the cosine function, and the e to the x function. For those particular Taylor and Maclaurin series, I do have an interval of convergence of all real numbers. The second case This case here is really our worst case scenario, is that f of x is equal to my power series for x equals some value of a. In other words, it only works for one particular value. Now, we've talked about how when we're dealing with the Maclaurin series, a is 0. But for a Taylor series, a could be any number on our number line. And it's really depressing, but there are some situations where the best we can do for a power series is a power series that equals our function only for one particular value on our number line. That also is fairly rare. But the most likely outcome is that f of x is going to be equal to my power series for x on some interval. And in general, our interval is going to be from a minus some value to a plus some value. And a is what we call our center of convergence. And we've been dealing with a lot with our Taylor series and with our Maclaurin series. R is what we call our radius of convergence. And this whole interval from a minus r to a plus r is our interval of convergence. And so if I have an interval of convergence that goes, say, from negative 2 to 4, the thing is my center of convergence, in other words, the midpoint of this segment, would be x equals a positive 1. And my radius of convergence in this case would be 3, because I'm essentially dealing with 1 minus 3 to 1 plus 3. So given an interval of convergence, I can determine a center and a radius. And if I have a center and some radius of convergence, I can determine my interval of convergence. And we saw this happen a lot when we were dealing with our infinite geometric series, this idea that the absolute value of r had to be less than 1. And in this situation, if I'm dealing with x being less than 1, then 1 is my radius of convergence. And if I'm dealing with some function of x, I ended up with either a larger radius of convergence or a smaller interval of convergence, depending on what the coefficient was, if the coefficient was larger or smaller than 1. So these are my three possibilities for convergence, and we're going to see this happening the most in our situations we're going to be dealing with in sections 9.4 and 9.5. It's really nice when it's the reals. It really is bad when all we can do is just have it for one endpoint. But most likely it's going to be a situation where we're going to be converging only on some interval including A. So I want to start by talking about two different tests that we have. And the first test I want to talk about is the nth term test. And the nth term test is a pretty basic test. It essentially says that if the limit as n approaches infinity of a sub n is not 0, then the sum from n equals k to infinity of a sub n diverges. In other words, if I'm looking at a limit and these terms are not getting smaller and smaller and smaller, if they are, say, approaching 1 or approaching 2, and if I add an infinite number of these 1s or 2s together, clearly I'm not going to get a converging sum. I'm going to get something that's divergent. And so I can do a real quick example of that. Let's say that I'm dealing with the sum from n equals 0 to infinity of n over n plus 2. Now, if I take a look at the terms of this series, the terms of this series are going to be 0 halves, 1/3, 2 fourths, 3 fifths, 4 sixths. And one of the things I noticed is that these terms are actually increasing. And if I look at the limit as n approaches infinity of n over n plus 2, we know either by L'Hopital's or by algebra that this limit is 1. And so that means that this series has to diverge by the nth term test. And what's going to be really important when we're writing our answers is it's not enough to tell me it converges or it diverges, but you're going to have to tell me what type of test you use to prove this. So let me do one more example of this. Let's take a look at the example where I'm dealing with the sum from n equals 1 to infinity of cosine n pi. And if I take a look at this series here, this series is essentially negative 1 plus 1 minus 1 plus 1 minus 1, etc. the thing is, these values are not getting smaller or larger, but in fact, the limit does not exist. This is one of those situations where the limit is in approaches infinity of this function does not exist. It's not going towards positive or negative infinity. It just simply does not exist because I'm essentially dealing with something that is either going to be a 1 or a negative 1, and there's no in between. Now, the real key thing here is that the converse is not true. Just because the limit is in approaches infinity of my terms of my sequence goes to 0, this does not imply that the sum of my terms converges. And there's a famous one that we're going to be dealing with a lot in the rest of this chapter. Something called the harmonic series, which is the sum from n equals 1 to infinity of 1 over n. Now, I know the parent function 1 over x, and as x goes to infinity, this limit does in fact go to 0. But what we will find in section 9.5 is that this series is unbounded. In other words, this series diverges. So just because the terms are going to 0 does not mean that I'm going to have a convergence sequence. All that I know is that if the terms of the sequence are not 0, then the series has to diverge because it's going to go to a positive or negative infinity. And that's the nth term test. The other test that we're going to be talking about today is the direct comparison test. In other words, if I compare two sequences, one unknown and one that has a very, very well-known behavior, then I can make predictions about what's going on. So there's two parts to this. The first part says that if A sub n is less than B sub n, for all values of n past some point, and I know for a fact that the sum of A sub n diverges, well, these terms are all bigger than this term. And if this sum diverges, then the sum of B sub n also has to diverge. And the second part says that if A sub n is always less than C sub n, is always greater than C sub n for n beyond some value of n. And my series in question converges. In other words, this comes out to a sum, every term here is smaller than this term. Then C sub n must also diverge. And I want to do a couple of examples of this to kind of talk about what's going on here. So let's say that I've got the sum of x to the 2n over n factorial squared, as n goes from 0 to infinity. Now I'm looking at this, and I'm looking at this term, and I know that if the denominator is bigger, then the fraction has to be smaller. So this has to be smaller than x to the 2n over n factorial. That's not squared, because a larger diameter is going to give, a larger denominator is going to give me a smaller fraction. But I know something about this sequence. If I take x to the 2n over n factorial as n goes from 0 to infinity, this is really e to the x squared power. And I know this from the Taylor series, that this converges for all n. And therefore, because this term is adding up terms that are smaller than the exponential series, this has to converge for all n. In other words, it's really convenient if I can find some way to compare it to something that's known. And as long as we are less than a known term, a known sequence, and we've dealt with 4 so far that work. If I can prove that each term of my series is less than another term in a convergent series, and that convergent series converges, then my series has to converge. Now, of course, that also means that if I come up with a series that's larger than the series that I know that diverges, then it has to diverge as well. So we'll do one more example. Let's take a look at this. If I take the sum from n equals 1 to infinity of 3 over n minus 2. Let's go ahead and make this sum from 3 to infinity. If I want to take a look at this series, and I want to know if it converges or diverges, I can take 3 over n minus 2, and I can compare to 1 over n. We talked about the harmonic series at the beginning of this lecture. And this is the one series that we have to memorize that diverges. And this comparison test is really going to help us understand this divergent quality. The thing is, I know that 3 over n minus 2 is always going to be bigger than 1 over n minus 2. And if I have a larger denominator, then I'm going to have a smaller fraction. But I know that the sum from n equals 3 to infinity of 1 over n diverges, because it's only 1 plus a half plus a third away from the series that goes from 0 to infinity. And so if I take off this, the tail must also diverge. And therefore this must diverge. So the whole idea when I'm using this direct comparison test is I want to compare it to something that I know. And of course I want to do a real quick recap of the ones that we've talked about. We've talked about the infinite geometric series. In other words, the sum of x to the n as n goes from 0 to infinity, which converges if the absolute value of x is less than 1. We talked about sine x, which is equal to the sum from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 power over 2n plus 1 factorial. And this converges for all reals. We talked about the cosine of x, which is the sum from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. And we know this converges for all reals. And e to the x, which is the sum from n equals 0 to infinity of x to the n over n factorial. And this converges for all real. So I could compare, and if my terms are always less than this, or less than this, or less than this, or less than this, then my series must also converge. So these are the 4 convergence series that we've talked about so far. And we also have one diverging series that we talked about. The sum from n equals 1 to infinity of 1 over n. And this diverges. So if I ever get a series where the terms are bigger than 1 over n, then that series must also diverge. Now, these are just two tests that we have to see if a sequence converges or diverges. And today's lesson really has kind of emphasized on the idea of finding a divergence series. In our next lesson, we're going to talk a lot more about finding convergence series, and also a lot more in situations like this, where I'm going to have not on all reals, but only on some narrow interval, some interval centered about some point A. So this is Mr. Potter. Thank you for watching. Have a great day.